we're in. So for these groups, the set of irreducible smooth G representations, again over FP bar, is unknown. I guess outside of the case when n equals 2. So if n is different from 2, then this classification is completely unknown and probably will not be known in the near future. But kind of the analogous thing on the side of Hecke modules, so simple H modules, is completely known. And this is due to work of Vineras, Olivier, and Abe. So if we allow ourselves to kind of pass to modules over the Iwahori-Hecke algebra, then kind of the analog of this question of classifying irreducible smooth G representations gets translated into classifying simple H modules, and this is something which we kind of know in complete generality. So even for groups other than GLN and SLN, so really any reductive group over any non-Archimedean local field. And so just to give you a flavor of what these look like, let me run through an example. And I'll do my favorite example. So this is going to be SL2QP. And I mean, I know most people are maybe more comfortable with GL2, but I prefer working with SL2 because the formulas end up being a little bit simpler. So I'm just gonna stick with that thought process. So let me remind you that this Hecke algebra is generated by TS1, so that's T1 minus 1, TS0, it's T minus P inverse P, and T of these diagonal elements, where X is in FP, so it's in the residue field. And by abusive notation, think of this as just a lift to SL2 with the relations that TW prime equals TWW prime if the length of W and W prime behave additively, which is not always the case, and that these TSI, when I square them, I get the following sum. So I get a sum of all of these P minus 1 things in the residue field times TSI plus Q -1, -1. And again here, I'm writing Q is equal to P. And that's because when one works with these things for more general p-adic fields, usually the size of the residue field is FQ, and that's the same Q that comes up. So this Q is the size of the residue field. And if you happen to read kind of representation theory literature, they often consider these types of algebras as well, and for them Q is often a formal parameter. So these are the relations, and maybe I'll just say, I didn't talk very much about kind of the affine Weil group or the Coxeter group behind the pro-P picture, but it works the same way. I can inflate the length function to the affine to this W1 tilde, and these elements get length 0. So that is almost enough to help you figure this out. Yeah, so this would be x over fq star, or over just the residue field. Okay, right, so then the simple H modules fall into 4 categories. So I'll just write them all down. And as I do this, you should keep in mind the classification of irreducible smooth representations due to Barthel-Livnay, where they have 4 kind of classes of representations. The Barthel-Livnay classification for GL2 kind of generalizes in the same way as SL2. So it's not so far off. It's either trivial, Steinberg, principal series, or supersingular. Okay? And you'll see kind of an exact mirroring here. Except for SL2, I don't have to worry about determinant twists. I don't have to worry about characters. So the notation is simple. Okay? Right. So let me tell you what these look like. So the first one is what's called the trivial character. Okay. So I'm going to denote this mtriv, and it's going to be a one-dimensional representation, so generated by a vector v with action. Okay, so maybe the first thing is, in the last lecture, I kind of wrote it on the board, but maybe didn't say it out loud, but kind of the natural way that this Hecke algebra acts on spaces of invariance is as a right action. So all of my modules are going to be right modules. That's one thing. And the second thing is, well, I also gave you a basis for this space, but I'm telling you that it's generated by these operators. So these 2 plus these p-1 operators. So in order to determine a module, I just have to tell you how those operators act. So that's what I'm going to do. So t s1 acts by 0, t s0 acts by 0, and t x inverse acts as the identity. Okay. So inside of this Hecke algebra, these operators generate a cyclic group of order p. Since they have length 0, it means that their lengths kind of multiply correctly. So at least when I restrict this relation to these, they just multiply. So kind of sending an element x to this element is actually a group morphism. And this is just a long-winded way of saying that the kind of diagonal elements have to act invertibly. So they have to act by some character. Okay, so that's the trivial character. It's fairly simple. The second one is called the sign character. So sign, again, it's one-dimensional with action v ts1 is minus v, v ts0 is minus v, and v tx x inverse is the identity. So minus v minus v. So maybe it's not 100% clear as I write it down like this, that kind of these things assemble correctly to give you a module. So for example, like the action of TS1 has to somehow respect this relation, but one can check that that is indeed true. Okay. 3, I'm going to call these principal series modules. And so here, I'm going to fix chi from qp star to fp star, which is a non-trivial character. And I'm going to set delta to be 0 if chi restricted to zp cross is non-trivial, and 1 if it is trivial. So delta just measures whether the character is unramified or not. So then m chi is going to be a two-dimensional space now. b1 plus b2 with action as follows. So this is going to be the most annoying one. So b1 t s1. Let me make sure I get this correct. This is b2. b1 ts0 is negative delta b2, no, b1. And b1 t x inverse, so right here, is chi x inverse b1. Okay. So that's the action on the first vector. And on the second vector, I get negative delta b2 b2 ts0 is chi of p inverse of b1, and b2 times this is chi of x b2. So a little bit more complicated, but still not the worst thing. But again, it's something one can write down very explicitly. And here, just to keep things, irreducible, I assumed that this character chi was non-trivial, but if chi happens to be trivial, then these formulas still make sense. It defines for you a module, and it happens to be irreducible. And you can check that it has a unique subrepresentation, which is the trivial character, and it has a unique quotient, which is the sign character.
So, it's chi smooth?
I'm sorry?
Is it smooth?
Chi is smooth, yeah. Everything is smooth. Then the last one, I'll call these super singular. So here, we're going to fix an integer r between 0 and q minus 1. Then m_r is again going to be one-dimensional with action. And now I have to split this up according to what r is. So if r is 0, then b ts1 is 0, b ts0 is minus b, and b tx x inverse is b. If r is at the other extreme, then I just flip these two. So this is minus b, b ts0, 0, and b x inverse is b. And if R is strictly between 0 and q minus 1, then the action of these elements is 0, and the action of this one is by a character, which is chi x, there's no chi. It's just x to the minus r. Okay, so again, I've written these down, and they parallel exactly what happens for the group representations. And again, that's no coincidence. Kind of the way these are built up is in complete analogy with what happens on the group side. There's even though maybe the principal series case doesn't look like it, there is a process of parabolic induction for Hecke modules that one can use to build those principal series. But here's the fact, or an exercise, if you wish, is that every simple H module is isomorphic to M-triv, M-psi, M-chi, or M-r, where for these, I'm assuming this is not 1, and for these, I'm assuming this. So it's not an easy exercise, but maybe one starting point is one can try to classify those simple H modules on which this torus part acts trivially. That's essentially the same as classifying modules over the Iwahori Hecke algebra instead of the Prof Iwahori. It just kind of removes this case and this case. A little bit easier. Right, and maybe I'll just say out loud, is that there's no kind of isomorphisms in between these. So if I take two distinct characters, these modules will be non-isomorphic. If I take two distinct R's, these modules will be isomorphic. And there's no isomorphisms between any elements from different families. Okay, so this is all just designed to kind of convince you that this is really hands-on. If I just gave you the presentation of the Hecke algebra and you sat for maybe a day or two, you could come up with this list. Just by using this generators and relations approach, maybe kind of saying something clever about the center. But this is all like quite doable, and one can do this kind of independently of knowing anything about group representation theory. So let me make.
So, excuse me. So this result is for GLNQP and SLNQP. This.
Say again.
This result, every simple H module is isomorphic to these 4 kinds.
Mm-hmm.
This is true for GLNQP and SLNQP?
So the analogous statement was that I can just write down a complete list of simple modules for any reductive group. So for GLN, SLN, symplectic group.
Always
really,
these 4 kinds?
Well, there's going to be kinds that are indexed by kind of parabolic induction. So I can either have a supersingular or something coming from parabolic induction, right? So first, let's say I classify the supersingular modules, which the word supersingular does have a definition on the side of modules. Then I classify these supersingulars, and then I can get those two by figuring out where these are reducible. So if I were to do something for GL3, I have more parabolic inductions to worry about. I can parabolically induce from the Borel or from like a 2-1 levy. So it's kind of stratified in this way by where I'm parabolically inducing them.
Just like that dimension of 1 and 2 of simple modules over a gave any reductive group. Is it?
So the dimension will be bounded. So any simple H module is going to be a finite dimension. If I take SLN, for example, then the supersingular module will all be one-dimensional, for example. It's not the case for GLN. So maybe I'll mention something about that in just a moment.
Orthogonal classification has to be very similar with respect to fuse for point 3, because when you have an unramified character, then you have this lambda, this from n is equals to, then you have a lambda, yes. But here you seem to have more characters because you're relying on ramified characters also. Are there some extra?
Well, one of the Barthes-Livne papers is in the unramified case, and the other one is in the ramified case.
Okay.
So that's,
But the classification
again, there might also be like a GL2 SL2 discrepancy because
compact dimension 1 G minus lambda, right?
Yeah.
Y or lambda is that you give
Yes.
series.
yeah, so the lambda always comes from here in the principal series case because it's a non-zero parameter. Yeah, and you have to just compensate. This character on this torus essentially accounts for the R in the sim R. So that's why the R is being used here as well.
Oh, so these characters are all in the ramified.
Yes, yes.
Much extra.
Yes.
So that's the R part.
Yeah, exactly. Yeah. Other questions? Okay, so maybe first remark. So I set up my notation kind of the way I wanted to with these Qs. So this classification works for SL2F for any extension of QP. Even though we don't know what the irreducible representations of this group are. Even though we don't know the groups. And so literally nothing changes. This Q is now the size of the residue field of this F, and this classification is exactly the same. I guess I have to take F star here and look at unramified characters, but it looks identical. Two, just to kind of tie it back. So we have a similar description for GL2, QP, or GL2F, if you like, of these simple H modules. They, again, fall into four families, kind of analogous to Barthes-Livne, except that the supersingulars have dimension 2. And again, the idea is if I kind of remember that I have a complete classification of irreducibles here, I can just look at their I1 invariants, and essentially this is how they will behave. The only issue is that when I work with GL2, there's kind of more parameters. There's these determinant twists that I have to worry about, and there's kind of isomorphisms between different principal series, and I didn't want to worry about that. So restricting to SL2 just simplifies the notation. And maybe I should say, I'll just repeat myself. This sort of classification extends to general G. So any reductive group it won't be, like I said before, it won't be 4 classes of modules anymore, but you can start to kind of build these modules starting from super singular ones. So either the thing you start with is super singular or it's not. And if it's not, it comes from parabolic induction from some smaller reductive group. And that's where I get these kind of principal series. And depending on how big the Levy subgroup is that I'm inducing from, well, that's the kind of thing that gives you a list. So I don't want to say any more about that. This is known in the literature. So on the Hecke module side, we sort of know all of the simple objects. So in that sense, it's a little bit better. Okay. Questions here? Okay, so this wasn't as much an application as maybe more of a demonstration showing that once I have like this explicit presentation of the Iwahori-Hecke algebra, I can really work with it in an explicit way. And again, somehow every simple module here is going to be finite dimensional, so it's maybe a little bit easier to wrap your mind around than some big infinite dimensional vector space. Okay, so let me move on to kind of the second thing, which is how we can go from H modules to G representations. So, and again, let's pretend we kind of clear our assumptions. So, given a simple H module M for GL2QP, there's a construction of Pascunas which associates to M what is called a coefficient system. On the Baruch tree. This is also sometimes called a co-sheaf. So on, I forget, do we have a notation for the Baruch tree? Okay, I'll just use curly T.
So we have used script A.
Script A?
A.
Ah, okay. I guess that's going to conflict with Andrea's lecture.
Yeah.
Okay. Right. So, well, actually, let me use T, because A sometimes gets confused for apartment, which is a part of the building. Okay, so I don't want to kind of go too in depth on this construction. But let me just kind of mention some features. And well, one of the reasons I don't want to go too in depth is because this is essentially the content of Mihir's course. So attaching these coefficient systems or constructing these coefficient systems. In Mihir's course, the kind of keyword is diagrams, and it turns out that a coefficient system is equivalent to a diagram. There's an equivalence of categories. But let me just give some idea of how this works. And I should also say that what I'm talking about here is kind of the original paper of Pascunas, before Breuil Pascunas. So these constructions are not necessarily more elementary, but they're less technical. Breuil Pascunas don't start with a Hecke module either. They kind of just build coefficient systems from the ground up. But there's a way where you start with a simple H module, and you associate a coefficient system. which again is just a collection of vector spaces or representations for every facet of the building. So this is either an edge or a vertex. And again, this is equivalent to a diagram which, okay, I'm going to ask again. What is the notation we were using for an edge? Do we have a standard notation?
Sigma sub 1.
Sigma sub 1? Okay. So this is the standard edge, right?
Yeah.
Okay. So this is the standard edge? Standard was what? Okay. And then we have an injection into sigma sub 0. Okay. Where this, the thing that I put on the standard edge is related to the restriction of M to these elements. Okay, so it's some character. And this is related to the restriction of M to these elements and TS1. So I don't, again, want to go into too much detail, but if I take my simple module M and I restrict it to these elements, it gives me a character of these xi's, so I can use that to build a character of the Iwahori. And here, if I restrict M to this subalgebra, then that's related to a representation of K by some recipe that I, again, don't want to go into. But there is a very precise recipe for constructing such a diagram, and then I get a coefficient system. And I'll tell you what the upshot is in just a sec. Okay. And again, these things are not complicated. They're, like, if I start with something simple, these will usually be simple representations themselves, irreducible representations. Which is different. I think in the Hughes course, these, like here, you get a sum of Serre weights, like a complicated combinatorial description. So this is a lot simpler. And so once we have this, we can look at H0 TCM, which remember is the co-kernel of compact induction. So yeah, I'll try to use the same notation. So K1 to G. So remember, this is the subgroup generated by IZ and what I've been calling omega. C M sigma 1. And here I have compact induction K0 to G C M sigma 0. Remember this is KZ. This map is delta. And what does delta do? So if I take G and V, I'm going to send this to G. So here, this map is an injection, but let me call it restriction from sigma 1 to sigma 0. This is the restriction sigma 1 sigma 0 of V minus G omega R sigma 1 sigma 0 omega inverse.
So one has to twist by some non-trivial character.
Here?
Yeah.
Oh yeah, I was forgetting where the twist was. You're right. So here I'd probably twist by mu minus 1. Okay, so I can look at this. This is exactly what showed up in the Hughes course. And so let me tell you what the consequence of this is. So the entire time this coefficient system, or this diagram, is built out of this module M. So the final result about this G representation. So again, the final result is that this gets a smooth action of G. So I have some smooth G representation. What can I say about it? Well, the following theorem, kind of tells you. This one? Here? Yeah, so remember, this has an action of this group. So it comes equipped with an action of omega. So if I have a vector in here, I can first act on it by omega. It lands back in here, and then restrict.
So it's not the denominator.
It's not what?
It's not some kind of denominator or something else. I mean, it's like D1 and D0, you just take D and the inclusion. You refer to some action on the left and then yours.
So I can build these two actions independently, actually. I mean, if I'm being very precise, then what I'm doing is restricting to this. So I have this extra heck operator here that tells me how to do the involution. Yeah. Right. So the theorem, plus kunos, is that if M is a supersingular H module, which, again, I haven't really told you what a supersingular H module is, but you can kind of imagine that it's something that should correspond to, It's something that should correspond to a supersingular representation. And again, there's a purely intrinsic definition in terms of H modules. Let me go back and correct something. Here, I'm actually going to go with GL2F. Everything I've said works for an arbitrary F. Yeah, it's important that I do arbitrary F. So then, this representation. So in general, this representation is going to be very big and hard to control. But what Pascunas does is he shows that this has an irreducible admissible quotient, which I'm going to call V. Okay, so this is sort of a general fact. What can I say about this V? So I've constructed some irreducible admissible representation. So moreover, if I look at VI1, this is going to contain this M. So H is the simple module I started with, and then out of that I build this coefficient system, and I look at its homology. And just like with this diagram business, it gives you a G representation. Yeah. Yeah. I mean, it's the same thing as when you build a diagram. Like there's this H0 construction that gives you the G action. I mean, when you take these compact inductions, these are both G representations. So the co-kernel will also be a G representation. So what you get in the end is an irreducible admissible V that contains M. And therefore, V itself is supersingular. as a G representation. So Pascunas' first paper constructs many of these supersingular representations of G for the group GL2F. So we're going beyond GL2QP with this construction. Right, what should I say? Note, however, that kind of by global considerations, namely looking at kind of the expected compatibilities with cohomology of Shimura varieties and things like this. These V, well, let me be optimistic. I'll say might not participate in a local Langlands correspondence. So what do I mean by that is that anytime I construct any sort of correspondence, or anytime I construct supersingular representations, I want them to be attached to simple or irreducible Galois representations. And I want that kind of matching to respect some sort of global setting. So the global setting, I look in some cohomology of Shimura varieties, and I want to see this local Langlands correspondence appear in there. So for GL2QP, this is the case. It's a result of Emerton, that Broy's local Langlands correspondence shows up in cohomology of Shimura varieties, which is a global thing. There's some adelic part and some global Galois part. But these representations, these supersingulars that I construct, somehow they're a little bit too small in a precise sense. And in a more precise sense, they have the wrong Serre weights to participate in a local Langlands correspondence, at least in the naive way. So these, we are likely not to see them inside the cohomology of Shimura varieties. So whether or not they actually contribute to a local Langlands correspondence is still kind of up in the air. Whereas the supersingulars from Broy-Pascunas, we know actually do show up in the cohomology of Shimura varieties. So when Pascunas first came out with his paper, again, this is in some sense a less involved and less technical construction. Everybody was quite happy because he constructed all these new supersingulars, but then it turned out that they might not be kind of the right ones to consider. And this is kind of a more, I guess, philosophical statement. I'm happy to talk about it more off the record. And then, maybe for those that are following along, proving that this representation that I get, this irreducible admissible thing, actually is supersingular. The strategy is to find this supersingular module inside of here. Because things like principal series are not allowed to contain supersingular modules. This is different than Mihir's talk, because in Mihir's talk, he constructed some diagram and was able to compute that this space of invariance has dimension bigger than 2. And that's how you show supersingularity, because anything that's not supersingular has dimension bounded above by 2. So it's a different strategy to show supersingularity. And it's 2-dimensional, yeah. No, I mean, VI1, we actually, in this construction, we don't know how big this is. But we know for sure that it contains M. And it's finite dimensional because of admissibility. But, I mean, it may well be 2-dimensional. So in Mihir's lectures, to show supersingularity, you just show that the space of invariance is bigger than 2. Here we don't know, but we know the other piece of information that it contains this M. And that guarantees for you supersingularity.
So in this case, to show that M is super singular, V is super singular, you need to find some super singular module M which is inside VI1.
Yeah, that's equivalent.
So there can be some super singular dimension
Yes.
GLQP.
right.
Yeah. And perhaps for GL2F, there might be these as well. Other questions? Okay, so now I want to stay in this.
So therefore, it's not clear from what you wrote on the board. Or is it clear? Oh, just because it has a super singular.
Yeah. Okay, so now I do want to stay in this realm, and now I'm going to specialize the GL2QP. And kind of say what else we can do. So, so again, often when we specialize to GL2QP, we can get even more information. So this is a theorem of Olivier, which says that if G is GL2QP, and by the way, I think this has been proved kind of in various ways, so there might be more than one attribution here. So maybe I'll write let G be this, and be an E rep of G. I'm going to let CV denote the coefficient system attached to the diagram which looks like VI1 injects into the K representation generated by VI1. So now I'm starting from a diagram. So again, this is, I could also take something like K1 invariance here, the principal congruence subgroup. That gives me a diagram. This is another example of a diagram I can take. And then the result is that if I look at this representation, so I take this coefficient system, do this exact same procedure, constructing this, then this is actually isomorphic to the original V that I started with, which I can rephrase, and that V admits a resolution which looks like so I have the compact induction from this subgroup G, VI1 tensor mu minus 1. This goes to the compact induction KZG, K VI1. This goes to G, and it goes to T. Okay? So this says that any irreducible representation of GL2QP admits such a resolution. And again, I'm pretty sure this was proven by many other people. I think Colmez has a proof. But the proof of Olivier uses this kind of setup with coefficient systems. And so the proof here uses this equivalence of categories. And maybe I'll just mention that this gives an example of what is called a standard presentation. of V in the sense of Kolmaz. Actually, okay, maybe I'll need to check this, but I don't think you even need to take irreducible here. I think you can really take any representation of G and get such a resolution. So what does this standard presentation mean? Well, it essentially means this, that V has kind of this two-step resolution by something that looks like this. But this kind of resolution was used by Kolmaz in his construction of the p-adic local Langlands correspondence. So he needed to know that representations kind of admit such a resolution to be able to apply this function. So this is all kind of tied in.
I have a question.
Yeah.
So in this previous setup, you could have done this Askuna's theorem for SL2F also.
Mhm.
In that case, it was just one-dimensional, super singular.
Yeah. So what is the question?
No, the question is, so it's there. One can also get SL2F super singular by the same.
Yeah, so I thought about this in an earlier paper of mine, and to do this kind of setup, I needed to impose extra conditions. So I needed to assume that the residue field was there. It seemed like there was some combinatorial things that I wasn't able to work out when the residue field was bigger than FBA. And it had to do with these injective envelopes at finite level. So, I mean, I also thought about this like over a decade ago, so maybe I have some better ideas now, but it is possible to do this for SL2, except it behaves a little bit differently.
The other diagram, just take K1 there.
Yeah.
You not take the 0 back to V, or you
So this is going to be equal to VK1 if you have like a principal series, but if you have a super singular, then it's general different. Yeah.
actually won't H0 is equal to V.
Sorry?
The conclusion that H0 is more big to V.
I don't think that holds anymore. I think it's hard to identify. Other questions? Okay. Right, so I guess this kind of first application gave you some examples of Heka modules. This construction requires kind of a precise knowledge of these Heka modules, but again, they're relatively easy combinatorially. And this tells us how to go from Heka modules to group representations. The next thing I want to do is talk briefly about how to go from H modules to phi gamma modules. Okay. So again, let me reset things. So I'm going to suppose G is GLN QP. And like M, the an H module. Okay. So we're again going to use coefficient systems. So again, using coefficient systems, which again, you should just think of as some sort of sheaf on the tree. So for every vertex, you have a vector space. For every edge, you have a vector space. And there's some restriction map that acts compatibly with them. So again, using coefficient systems, Grossi-Clona associates to N a different coefficient system. So let me call it curly dm. And it's actually no longer on the tree, but on something called a half tree. So on t plus. So this is half of the Bruhat's tree. So starting with m, he gets this coefficient system. And again, m is a Hecke module for GLN. So really, I should be getting a coefficient system on some bigger object. And that bigger object is what's called the Bruhat's building. It's a much more complicated thing, but he kind of takes that thing, restricts it to some subcomplex, and pulls it back to GL2. So at the end of the day, he's really just working on GL2. But it's a much more complicated coefficient system than this CM. And so once we do that, we can look at H0 T plus dm. So what happened before when we were working in the GL2 case? Well, we had the full tree, and so we had like a full action of GL2. Now I only have a half tree. So I don't get a full action of GL2 because the full action of GL2 kind of allows me to travel backwards. So I can only travel in one direction. But what gross clone can do, there's still some like semi-group actions on this. They kind of push me up the tree. Okay, so this is no longer a grep. Or I guess GL2. Well, yeah, I'll just write grep. So it's not the representation of any group, but we can endow it with the structure of a phi gamma module. So phi gamma module is kind of one incarnation of a Galois representation. So there's this gamma, which is, I mean, it's not so mysterious, it's just isomorphic to ZP star. And this phi is just some operator that commutes with gamma, kind of acts as equivalence. So you can imagine that, ZP or ZP star? Let's stick with ZP star. So you can imagine that this phi is roughly equivalent to the action of P1. So this kind of element pushes me in the upwards direction on the tree. Okay? I don't have its inverse because I can't go down the tree, but I can go up the tree. And again, the definition of how this action looks is a little bit technical, so I don't want to go into it, but hopefully like these comments are plausible that when I kind of cut this tree in half, I can still get some sort of action like this. Okay, so what have I done? I've started with an H module on GLN and produced a phi gamma module. And so what does that do? It depends. So this seems to have gone up. So I'll state the theorem, and that'll kind of give more information about what kind of module it is.
What is the base ring?
Sorry?
What is the base ring?
The base ring is going to be, it's in characteristic B. So it's B. Okay, so here's the theorem. We can gross a clona. So I should also say that this construction is kind of completely functorial that he's doing. So again, let's let GL on QP. Then the map M goes to H0 T plus dm. So this gives me a P gamma module. And what I'm going to do is I'm going to compose it further with Fontaine's equivalence of categories. So this D Fontaine's equivalence of categories between phi gamma modules and representations of gal QP bar over QP. So again, I'm not going to explain this equivalence of categories, but the point is if I give you a phi gamma module over this ring, then that data is equivalent to the data of a Galois representation. Right, so this functor induces a bijection between supersingular H modules M of dimension n and irreducible n-dimensional representations of gal QP bar over QP over FP. So I have some functor, and it behaves, well, you can kind of explicitly calculate it, and it actually will induce a bijection between these supersingular modules and irreducible n-dimensional. So Grosser-Klone first constructs this functor, and then what he does, let's turn it off. Hello? Hello? It says it's on. Oh, there we go. So he first constructs this functor, and then he uses the explicit description of these supersingular modules. So the kind of explicit way of describing them, and proves that we have a bijection here. Yeah. Okay, that's what I'll say next.
One more question. In the last lecture, you had mentioned forward equivalence between the representations related by the eigenvalue.
Yeah, so I'll mention that as well.
Do you start with simple H module or it's
Yeah, maybe let's assume simple to be safe. I mean, it's an exact functor, so that should tell you everything you
Which paper was
need. It's one in Duke from, yeah, I mean, I think it says like, I think it's called something like from hypermodules to Galois representations. Okay, so maybe I'll kind of tell you what the next step of this is, as was suggested. So again, this is very nice because it not only gives you this bijection, but the bijection is induced by a functor. I'm not claiming that there's an equivalence of categories going on anywhere, because in particular, if I try to do the trivial H module and plug it into here, I'll get 0. But it still induces a bijection. So moreover, if n equals 2, so this is the case where we have kind of as much nice information as we want. So the composition going from an EREP of GL2QP, taking its I1 invariance gives me a simple H module, and then going to this H0, where this is a representation of gal QP bar over Q. So if I look at this composition, it's a functor that goes from representations of GL2QP to Galois representations. So this is Kolmez's local Langlands correspondence. Maybe up to a twist and a dual, like there's always a normalization in these things. Yeah, so this is something you can explicitly compute. So this construction of gross clona, when n equals 2 and kind of combined with all the other nice properties we have, actually gives Kolmez's local Langlands correspondence going through Hecke modules first.
This paper of those are going to be before Kolmez or after?
It's after.
I have a question.
Yeah.
Grossagona assumes AF is equal to QP in this bijection, in this theorem.
Yeah, he has to assume F equals QP. He has some results for GLNF, but again, there's some kind of discussion to be had whether that gives kind of the correct correspondence. I mean, again, it seems that like this picture is all very nice, but one has to decide what one wants out of a local Langlands correspondence. Kind of one guiding principle is that it should match with global things, and it's still kind of unclear where this picture fits into global considerations. Okay. So any questions on this? So again, I'm going a little bit light on the details of these constructions, mostly because they're very technical, but in the references, or the references that I'm citing, like things are quite well written. So you sit down and work through the details, like it's a good learning experience. Okay, so let me get to the final thing, which is extensions of G representations. Okay. And this is going to be, I guess, give you a bit of a flavor of the next lecture on derived things. So here I'm going to assume G is GL2QP or SL2QP. And in the examples I write down, again, I'm just going to take SL2QP because things are a little bit simpler. And so recall that we have an equivalence of categories between representations of G generated by the I1 invariance and modules over the Prof-Hecke algebra. So I've already written this category down, so let me not do it again. Okay, so we have this. And what we can do is we can actually use this equivalence to get some information about extensions in the category, in the entire category of G representations. Yeah, so exactly. So this bijection I can talk about kind of a numerical local Langlands correspondence. So work of Vigneros and Olivier showed that at least if I fix maybe the action of a uniformizer and the action of Frobenius here, then the number of supersingular modules of dimension n was equal to the number of these Galois representations. So it was some sort of numerical bijection. There was no bijection, but at least I had the same number of candidates on both sides. But this actually gives a map in one direction. And I guess if you want to use that numerical correspondence, it suffices just to show that this map is injective, for example. So you can always kind of prove things more numerically first. Okay, so I have this equivalence. So now let's suppose V and V prime are two representations of G. It doesn't matter which of those G's I take, such that V is generated by its space of I1 invariants. Let's see where I am. Okay, so out of this, it takes a little bit of playing around with category theory, but it allows me to construct essentially a growth indique spectral sequence which looks as follows. So the first thing I do is I look at x to I in the category of H modules of VI1. And then the second entry, I put HJ, so group cohomology of I1 with coefficients of V prime. And this converges to xi plus j in the category of G representations, V prime. Okay. So this is, if you want, it's essentially like a, well, there's a way one can think about this as like a Hochschild-Serre spectral sequence. But let me make a few comments. So, so we already discussed how, so let me do this parenthetically. So if I take V prime, I1 invariance, then this is a right H module. We discussed this last time. But the thing to kind of observe is that this is H0 I1 V prime. So this functor of invariance takes me from G representations to H modules. And what I can do is I can derive this functor. So just kind of by formal manipulations, I have that the higher cohomology is also a right H module. So this is kind of completely general, but one can actually make this action explicit. It's not actually so mysterious. So just by kind of deriving this functor, I can get this. Yeah, I guess this is going to come up in the next lecture. But I mean, somehow there's a lot of functors floating around, and like kind of taking a more functorial approach to all of these things. You might have noticed, but kind of the basic functor at play here is this functor of invariance. And in general, it is not exact in this category, so it is generally good practice to try to derive this functor. And when I derive it, I get something that I can actually recognize. It's just group cohomology. Okay? And I can use all the tools of group cohomology to try to understand what this thing is. So the idea is that if we want to compute x to n in the category of G representations, which I'm going to kind of try to impress upon you that this is a hard thing to do, we can compute Hj I1b prime for all j, and xihb for all I, which maybe, at a first glance looks easier. Again, here, this is group cohomology, so there's many tools I have at my disposal. There's various spectral sequences, there's inflation restriction, all of this stuff. And here, and again, H has kind of a simple combinatorial structure. So maybe one can hope that calculating these X groups is a little bit easier. And why is this hard if I wanted to kind of just stay in the G world and try to compute this? Well, to compute an X group, I would, kind of from first principles, have to find either a projective resolution of V. Those don't exist. There's no projective objects. Or an injective resolution, but injectives are quite big and inexplicit. So it's almost impossible to write down an injective resolution of V. So already from the initial definitions, we know that this thing exists, but it's really hard to actually get your mind around. Okay. So this is kind of the state we're in. So this is what we're going to try to use to calculate these X groups. So let me give a theorem which Pascunas proved in the GL2 case, and I guess I wrote down in the SL2 case, which says that if V prime is an irreducible representation of G, well, let me write down the short version and then I'll give an example. Then we can calculate all Hj I1 V prime. So for all V primes and all J's. Okay. So it really is something quite hands-on. Okay, so I think I should have exactly enough time to do this. So let me give an example, and again, the notation gets a little more complicated for GL2, and there's kind of more degrees of cohomology to worry about for GL2, so I'll stick to SL2. Maybe try to convince you that this is, again, quite explicit. So let's do SL2QP. Again, I've told you that these are hecamodules, and I've written down all of the simple ones for you, so I can use that same notation. And here, I'm going to have to assume P is bigger than 3. So if V is FP bar, the trivial representation, well then, H0 of I1b, so that's just the I1 invariance of the trivial representation. And again, the notation is chosen a bit carefully, so if I take I1 invariance of the trivial representation, I get the trivial ecomodule. H1 of B is a principal series ecomodule for a character called alpha. And so what does alpha do? alpha is the character from QP bar to FP bar, which takes x to x squared, the p-adic absolute value of x squared. So if I do this, it basically takes away all powers of p. I'm only looking at the part in x that's the unit, and I look at that much. Then H2b is again a principal series Hecke module. H3 is again M trip, and then all others are 0. So again, one can write these down quite explicitly, along with their Hecke actions. So even if I, didn't think about the Hecke action, I could actually write down the dimensions of these for you, kind of from, using tools from work of Lazard on the cohomology of p-adic analytic groups like I1. So the dimensions are 1, 2, 2, 1.
The alpha part is atomic vector squared 1.
Exactly. Yeah. I mean, I prefer using the notation alpha bar because as a character on the torus, it's just the simple root. Right, let me give you another example. So these things can get a little complicated, but it's still quite doable. So if B is now a principal series for some character chi, so chi, again, character here, then H0, I1b is just M chi, the principal series Hecke module corresponding to chi. So again, this notation was set up so that when I take I1 invariance of this, I get the principal series Hecke module. H1 is a little more complicated. So it's now 4-dimensional. It has M chi sitting as a sub, and then there's an extension with M chi inverse alpha bar, check. So again, I think this notation showed up in Mahir's lecture. A dash means there's a non-trivial extension. So there's a filtration where this is the sub and this is the quotient. And here I just have to take some sort of dual. And then H2 is just chi inverse alpha bar. And then all others are 0. And so you can kind of proceed in this way, and the super singulars take a little bit more work, but it's quite hands-on. So if I give you any two irreducibles, then it's possible to kind of plug them in to this spectral sequence and get what you want. So let me state the theorem. Yeah, so I mean it's somehow even better. These groups satisfy a form of Poincare duality. Right, so in that principal series example, here I said the dimensions were 1, 2, 2, 1. Here the dimensions are 2, 4, 2. So plus unas, and then I think Madam Polly worked out some x1s, and then kind of the rest of the xn's I was able to do. So yeah, let me just state it informally. So using these calculations and the spectral sequence, we can calculate xn in the category of G representations, B prime, for all E reps B prime. So that's kind of the, packaging all of the results together, is that if you give me any two reducible representations, we can calculate these X groups, at least the dimension of these X groups, for all E reps, and maybe I should say all N greater than 0. For SL2QP or GL2QP. And again, the spectral sequence uses the equivalence of categories. Okay, so I'm almost out of time. Let me just write down kind of a sample result. So, example, again, I'm going to stick to SL2QP, but it's not hard to do it for GL2. So let's say I pick a character. Right, so a character from QP star, from FP star. So if chi squared is different from alpha bar, then I can look at xng of the parabolic inductions. And what are these? So I'll just write down the dimensions. So the dimensions look like 1, 2, 1, 0, 0, and so on. So these are the dimensions for n equals 0, 1, 2. So x1 has dimension 2. If I take chi here, and I take chi inverse alpha bar, well, then the dimensions look like 0, 1, 2, 1, 0, 0, and so on. And if xng, if I take int bg against any other character other than chi or this twist, so psi, here, psi different from chi inverse alpha bar, then this just equals 0. Broken. And maybe since I'm at time, I'll stop here, but we can also evaluate the case when chi squared is equal to alpha. The formulas are a little bit different. I think then it goes either 1, 3, 3, 1 or 1, 2, 2, 1. But that is also doable and covers all possible cases. That it's not equal to one of these two.
So these X groups are not Heka models.
these X groups are not Hecke modules, no. So they're just FP bar vector spaces. I mean, it's occasionally possible to kind of write down a representative. So, like if I take extension of Steinberg by trivial, then there's the induction of the trivial character that represents that class in X1. But yeah, right now, this only tells you about the dimensions. Okay, so maybe I'll stop here. Happy to take questions.